And the final speaker of this session is Bonnie Zaire, and she will talk about multipolar and dipolar dynamos.
And the charger. Oops. Why don't I have the presentation mode? Yeah? Well, it's okay. Not really. That's okay.
Try this one. There we go.
Okay, nice. Thank you. Okay, so hi everyone. My name is Bonnie. Right now I'm a postdoc in Brazil, in UFMG. But the work I'm going to present was mostly developed in France, Europe. So I want to thank the organizers for having me here, and also the Isaac Newton Institute and the Cambridge Philosophical Society for funding my visit. So today I'm going to talk about a paper that we recently published, Transition from Multipolar to Dipolar Dynamos in Stratified Systems. So this slide was mostly already introduced by Antoine Victosi. So just as a little curiosity maybe, as you know, like we know that the sun is magnetic since 1908, but only 80 years later we actually had the detection of the magnetic field for another low mass star. So since then we have about 30 years of a technique that can recover the large scale field at the surface of low mass stars. And we have about 100 stars, as Victor C. showed many results for us yesterday. So if we look for these results from this analysis that basically does an inversion process going from spectropolarimetry data to large-scale surface magnetic fields, what we can see from the surface magnetic field strength is this. So basically we have here several stars reconstructed with this technique, and we have the field strength compared to the Rossby number, which, as Antoine mentioned, is by observers computed as the rotation period divided by the convective turnover time. So if we do that, we see two clear regimes for these low mass stars, which have always outer convective envelope. We see basically the influence of the rotation in this dynamo that's operating this outer convective zone. So what we see for these low mass stars is that for high Rossby numbers, we have this unsaturated regime where reducing the rotation period of the star powers this dynamo and increases this magnetic field strength that we observe. But then below a given Rossby number of about 0.1, we see that there is this saturated regime where we see magnetic fields that have more or less the same field strength. So the other question that we could make is, if the field strength has this behavior with the Rossby number, could we see something similar, for instance, for the magnetic field morphology of these stars? So in other words, is the Rossby number changing the magnetic field morphology that we see? So if we look now for this so-called confusogram, because there's so much information here, it's kind of like a combined information of everything Victor told you about yesterday. So basically, we are going slowly here. Each dot, it's a different star, recovered with Zeeman Doppler imaging. So we have many information about the large-scale field. Here we have the rotation period of the star and the mass of the star. Basically, stars that are below this gray line here, they are fully convective. And stars that are above are partially convective. So we have this radiative zone and then a convective outer envelope. If we look for this, each symbol is telling us something. So we have the size, it's linked to the strength that was derived for the field in the Zeeman Doppler imaging. And then we have the color telling us how much poloidal this field is. So dark blue symbols are fully toroidal, and dark red symbols are fully poloidal. And then the shape is telling us how much axisymmetric this field is. So basically, the more round, the more axisymmetric. So I know this is a little bit confusing, but I just want you to retain the main points, which is, if we look for fully convective stars below here, we see that we tend to have strong poloidal fields, mostly axisymmetric. In other words, these big round red circles. While if we look for these partially convective stars, we have these weaker fields, and that often are dominant by toroidal fields. So this already shows the impact and the influence of the internal structure for us on the dynamo that's operating there. But now, if we look, for instance, for the Rossby number, which is what I proposed to look at the beginning, we have here isocontours of Rossby. So 0.01, 0.1, so below here, the saturated regime, above here, the unsaturated regime. We could perhaps say that we have a tendency of having more simple poloidal fields below here, but in fact, we can find several outliers. So you could also try to explain this as some bistability or something like that, but when you look also for high Rossby numbers, you see simple configurations with this poloidal axisymmetric fields here. So it seems that the Rossby number by itself, it's not sufficient to explain the geometry of the field that we see in stars. So let's see what we can learn about this magnetic field morphology from numerical simulations. So right now I'm going to talk only about 3D simulations that simulate a rotating convection in a shell. And we are only looking for simulations that amplify magnetic field, they are self-sustained, and we are analyzing the steady state. And we are going to define the magnetic field complexity following most studies for the Earth, which is defining the dipolarity, which is this quantity, that's the field strength in the axial dipole, so basically the dipole aligned with the rotation axis, divided by the field strength truncated at a given order. So basically here we are going up to L equal 10, which is reasonable for stars because we can reach, depending on the conditions of the star, we can go from order up to 5 and up to 15. So 10, it's a good range to truncate our simulations. As Antoine mentioned yesterday, we have to compare apples with apples. So if we look for that, first starting with Boussinesq simulations. So we have here the simulations of Uli in 2010. We have a constant density, and we can see clear 2 branches here depending on the Rossby number. So we have a dipolar branch for a Rossby number roughly below 0.1, and a transition to a multipolar branch as inertia starts to play a larger role in these dynamics. But recently, as it was mentioned also in early this week, it was found by Melissa Menou and collaborators in 2020 that also for Boussinesq simulations, so constant density, that if you increase the magnetic Prandtl number, you are actually playing with this force balance. And when you start to have important significance of the Lorentz force in this force balance, you can recover dipolar solutions even in this multipolar branch where you should not expect it from early studies. So you can see here, for instance, the highest magnetic Prandtl number of 5, and dipolar solutions started to kick in this more higher Rossby numbers. So, but we know that stars have strong stratification, and now we want to see how this scenario will look like for stars, or for stratified systems. So Thomas Gastine, back in 2012, approached this. So what we have here is, again, the dipolar fraction against the local Rossby number. And we have now stratified cases, and we have here, for different symbols, different levels of stratification. So if we start with this low stratified cases, so these reddish symbols, we can see, again, this transition from a dipolar branch to a multipolar branch. So this seems to work in a similar fashion to the Boussinesq. But then, as soon as he increased the stratification to higher values, so n were equals 2 and 3, he observed this collapse of the dipole. So at first, it seems that dipolar solutions are harder to obtain for higher density contrast, but we know that Hakesh Yadav obtained a strong dipole for low Rossby number with high density contrast. So it was lying at low Rossby number here. So it seems that's only harder, but you need to play around with this in order to obtain strong dipolar solutions. So what we wanted to do here was to approach with 3D dynamo simulations, the proposition of Melissa and collaborators and play around with this importance of the Lorentz force. So what we did, we used the magic code to perform 42 simulations. We considered 3 different density contrasts in order to see how increasing stratification would also change our results. And we varied the Rossby number by increasing the Rayleigh number. So we solved the MHD equations, and we played with the Rayleigh number to vary the Rossby number. We fixed Ekman to, we used the outer radius as the relative length scale, but in normal, using the shell gap, it will be something around 10 to the minus 4. We had a PM high equal 5, which was the value that was beyond which we started to have a significant importance of the Lorentz force in the force balance. And we also had this nearly adiabatic ideal gas that was fixed, that had a fixed background entropy gradient of -1 in order to force convection throughout our domain, which is slightly different from previous works. So what we obtained for the dipolarity against the Rossby number was, so we have here the 3 density contrasts, the weakest in red and the highest in blue. And we can see here, we categorized our simulations in dipolar and multipolar following the threshold of 0.5. So whatever is larger than 0.5 is dipolar for us, which means also more than 25% of the energy stored in the dipole. So we observed that we didn't have this transition for higher density contrast, but we did find it for our weakest stratified case. And if you look for the highest stratification case, we can see this nice dipole showing up here at a Rossby number of almost 0.5, and then transiting to a more complex solution. So also for our simulation, similar to what was proposed, we didn't find this nice transition with the Rossby number. So it really seems that we need something else to explain the magnetic field morphology in these anelastic simulations. So we tried to classify with the Rossby number, which is the ratio between inertia and Coriolis. But now we want to explore the other contributions in the momentum equation. So if we follow now for each of our simulations, we have here on the top the simulations with the weakest density contrast, and on the bottom, the simulations with the highest density contrast. So each Rayleigh here is a different simulation, and we are looking for the force contribution that at a specific scale, that's where the kinetic, the poloidal kinetic energy peaks and has the highest intensity. So if we look for the force balance at that specific scale, this is what we get. So basically what we see is that at first order, Coriolis, which is in black, and the pressure force, which is in blue, they are basically matching each other. So we have a geostrophic balance. Then at second order, we have the adiastrophic force in gray here. We can see that it's mainly balanced by the Lorentz force in red and the buoyance force in green here. And sometimes inertia is playing a role in this. And what we observed is that this importance seems to be relevant for transiting between dipolar solutions and multipolar solutions. So again here, multipolar solutions are represented by a cross and dipolar solutions by a circle. So we can see how as soon as inertia kicks in this force balance, we start to have these complex solutions. So we try to take this ratio and see how this would sort out our complexity, the magnetic field morphology. And we found that indeed, for our simulations, we can find a nice transition around this ratio of 0.4, which is slightly different than the ratio that was found by Tassin in Buzinesque's studies too. So the problem is that this ratio is not very convenient for observers because we cannot use this to compare with stars. So the next exercise that we did was to try to approximate this inertia over Lorentz force ratio by the ratio of energies in the kinetic motions and the magnetic energy. So when we tested this, we also found that there is a nice transition here, proving what was shown by Tassin also in Buzinesque simulations. And then we wanted to compare this with observations. So what we did next was to try to approximate the magnetic field energy using the Zeeman Doppler imaging maps that we found for a couple of stars. And we approximate the kinetic energy using the stellar models to obtain the photospheric velocity and the turbulent velocity at the near the photosphere. So if we use that to compute the ratio, this is what we found using observations. So basically, we are limited here by a sample of stars which have more or less the same convective zone depth and that are more or less comparable to our numerical simulations. Of course, we don't reach the precise value of stars in our simulations. So what we see is that there is a nice transition in the dipolarity as soon as the magnetic energy starts to become more important. We recover these dipolar solutions here, and this seems to sort out the configuration in the stars. So that was a nice result, and we also wanted to observe how our simulations were, what they were showing in terms of differential rotation compared to the magnetic morphology that we observed. So basically here we have the shear, which I computed as the average near the surface at the equatorial regions minus the average at the surface at polar regions. So if we take this, what we observed in these simulations was that for anti-solar differential rotation, we actually had these more dipolar solutions. And as soon as we got like a solar-like differential rotation, we lost this dipole field. So, but what we observe in stars, in fact, we also are very limited by the number of stars that we have this kind of information. We found that, in fact, there is no anti-solar differential rotation observed for these stars. And in fact, the transition, it seems to exist, although we only have 2 points here, but at positive differential rotation, so which is not in agreement with our simulations. So the main takeaway messages are we obtained for the first time stronger dipolar field configurations at high Rossby number for stratified systems. So this goes in alignment with what was found by Tassin and Menou. We also found that this ratio between inertia and Lorentz force is destabilizing, in fact, describing this multipolar transition. And we proposed this ratio of energy to be able to classify these stars in a way that we can still compare with observations and incorporate the physics behind this dipole collapse. So in our simulations, we found also a clear relationship between anti-solar differential rotation and the emergence of dipolar fields, which is not something that we see in stars in that way. So that's something to be explored. And thank you.
Thank you, Bonnie. And we have plenty of time for questions.
Thank you very much for this talk. I have a comment actually and a question linked to my comment. When you consider anelastic simulations with a density contrast, moderate density contrast, but it is possible in numerical simulation, of course, because the density contrast in models, in anelastic models, is far from a realistic one by several orders of magnitude. It's not very surprising actually to find the same result as obtained with Boussinesq model, because as you mentioned in the limits, when your n rho is equal to 0, it's similar to a Boussinesq model, so it's not surprising to obtain the same model. It is why I was wondering, did you find some new results resulting from the compressible effects from anelastic approximation in your model?
So actually, I mean, even if you have lower density contrast, you don't expect to have exactly the same behavior in the emergence circulation, in the differential rotation, and these kind of things. I didn't see, for instance, like I saved some backup slide here. I didn't see the differential rotation profiles, for instance, in those Boussinesq results, but for instance, our differential rotation shows nicely this this solar-like differential rotation increasing, although because of the large Lorentz force, we have a quenching in the differential rotation. So this is the relative differential rotation, and we see that's about 1% only. But we see this differential rotation increasing as we increase the Rayleigh number. So, and also we expect actually that increasing the density contrast is actually going to change the results compared to Boussinesq. So I don't see why they would be the same. Most stellar simulations, they reach like when they are very heroic, they are going to reach like n rho equals 5. So I don't know if I addressed your question.
We had a question in the front. So first Uli and then Johannes.
Well, thank you for the nice talk. When you started off by showing this nice diagram of magnetic field strength in the large-scale field versus Rossby number, which seems to be fairly well established. So I wonder, did you also look at, in your simulations, at the total energy in the large-scale field versus a Rossby number? Or did you only look at geometry and didn't worry about total field strength?
So I checked that the magnetic field energy was not dropping to like very low levels, but I didn't see any significant trend in the... Do you mean like if we could, for instance, recover some...
We could use this trend saturation, but then drop off at a large Rossby number.
I've never seen any code that's capable of reproducing that now till today. I don't think there is any work on that. You can recover, I mean, you can vary, but you can do like a variation parameters that's actually recovering the unsaturated and saturated phase.
Just to make it clear in my head, so you recovered dipole-dominated dynamos where previously there were none?
I'm sorry, I didn't.
You recovered dipole-dominated dynamos where previous were none in the strongly stratified cases like N-3, right?
Yeah.
It was very hard to find any. And now you find them, and the reason is that you have a stronger Lorentz force?
Yes, so
and
this...
because you increase PM? Is that understood? Did I understand that correctly?
I increased PM.
PM, yeah.
So
is that why you get a stronger Lorentz force?
So this is the same results that were actually obtained in Boussinesq. It was not a new idea. But there are other ways of obtaining these two. For instance, like Rakesh Yadav, he played around with other parameters, such as the Prandtl number.
Yeah, but I'm asking for new simulations. So what did you change?
Just the magnetic Prandtl number. So
yeah,
I also had like a comparison with the Thomas Gastin paper, because it's actually the same setup, same Ekman number, same Prandtl number, and then I boosted just the magnetic Prandtl number, and you can see how this changed the solutions.
And the Lorentz force then changes the zonal winds? Is that what I...
The Lorentz force
changes the zonal winds?
Yeah.
Is that what happens?
So we
and
also...
therefore, it becomes dipolar? Is that the line of argument? I just try to get it clear in my head.
Yeah, so the differential it's strongly quenched in our simulation. So it's everything in the order of 1% at most. So compared to other cases where you have lower magnetic Prandtl numbers, in that sense, yes, you will quench drastically the differential rotation.
Any further questions? Okay, I still had one question, and it's about the low Rossby number cases. So you tend to land on this dipolar branch every time you have a very low Rossby number. Have you ever seen large-scale non-axisymmetric modes, low-order non-axisymmetric modes in this regime, like M=1 magnetic field?
Like
cases?
this, you mean this totally non-axisymmetric case here, like with very low Rossby? You mean like that one? I have one simulation.
Is it like then dominant M=1 mode that you have excited?
but it's not L equal 1. So
Okay.
if it's not like an equatorial dipole, is that your question? Like if it's L equal 1 and equal 1?
Right, exactly.
No.
Okay.
So it's
Thanks.
more complex than that.
Okay.
So for all the simulations I tested that I have the same trend when including only the axial dipole and if including more axial or equatorial dipoles. And it's the same trend for these simulations. But we also have flipping dipoles.
Okay, thank you. So let's thank Bonnie and all the other speakers of the session. It seems that the speakers were also very hungry for tea, so now we have plenty of time for tea. So we reconvene at 4 o'clock.